I put up that link during spring break. So I would request you to everybody to try to write something. So at least 100 people should participate. Oh, you have a question?
Yeah, sorry. I was wondering if there's a possibility of slightly changing the deadline for our next assignment because it's due
Where
the day.
is it due?
It's due on Monday the 12th, which is the day we come back from spring break. Could we change it so we can have like some time to talk to the TA if we work out over spring break?
But yeah, you can, if you are in town, you can come during spring break also, because I will be available. But if you are not in town, then, so when was it due? On 12th?
I thought it was the 16th.
No, it's 12.
It's 12.
Oh, this might be bad. Oh, this is bad again? So if it is due on the 6th, so 19th, maybe 19th? Can we do 19th?
Yeah.
Okay, so I'll post an announcement. So assignment 2, you will have one more assignment. So 19th is fine, I think.
Yeah. Really cool.
Okay, so we'll have the second assignment due on 19th. Any other questions you have? Oh, by this week you get the grades. I think by Wednesday or Thursday. Okay, I don't know how it's just gone. So again you have to use the board. I don't want to because there is no documentation. But that's fine. So anybody has any problems regarding the Lamport's Bakery algorithm? Do you understand? Do you want me to go over it again? Lamport's Bakery algorithm, the one that we just discussed in process critical section. So let's just revisit that algorithm briefly, and then we'll go with the next topic, which is semaphores. So the basic idea in Lamport's Bakery algorithm is that any process that tries to execute critical section has to first ask for a token, and that token is asked in the second line. Second line of code is asking for a token. Then what you do is you look for all the other processes that are there, and you look through all those processes and see which one has a lower token than a given process. So let's say a particular process comes in, process I tries to execute critical section. It selects a token, and then it looks for all other processes that have a smaller token than process I. So smaller token number than process I. Now if you have a smaller token number than process I, then process I waits for the other process, whichever has smaller token number. Now if you have the same token number, then process I gives precedence to any other process that came before the process I. So it will wait for process I minus 1, it will wait for process I minus 2, and so on. So that is the idea behind this Lamport's-Baker algorithm. And then in the book, as another student was telling last class, that there is an elaborate proof, and mathematically you can show elaborate proof, but conceptually the proof of having mutual exclusion is not that hard. So what is the proof here? The proof is whenever a process tries to enter, it checks two things, token and the process ID. Yeah. Now the way token is selected, if two processes are slightly off, they don't come at the exact same time. If they are slightly off, then they will definitely have different tokens. Because token is max of num plus 1. They will definitely have different tokens. But if they come at the same time, they might have the same token. But then they will never have the same process ID. So at least one aspect, either the token or the process ID, at least one of that is different. So whenever two processes come together and try to execute critical section at the same time, there is no way that you can mistake process I and process J, because I and J are not same. They will have at least one thing different, either the token number or the process ID. Since they have at least one thing different, only one goes through. So conceptually the proof is very easy, but you have to, whenever it comes to mathematics, you have to define lemmas, you have to define theorems. So in the book there is an elaborate proof using mathematics. So you don't have to understand that. But for your own good, you can read it. If you are interested in theory, you can read it. But I won't discuss it in class. Now the problem was when we said that when we talked about Lamport's-Baker algorithm, we said there is a problem. There is a clear mismatch between theory and implementation. What is the mismatch? In theory, we assume that a process, or when two processes come at the same time, in theory we are assuming that they select the number and then go into checking each other. But that may not be the case in implementation. In implementation, what can happen is that if process I and J came at the same time, then it might so happen that process J, let's say I is less than J and J is greater than I. So process J can go select the maximum, select the token, and go and check all other processes, while process I only calculates the token and doesn't store it. Right? So process I calculates the token but doesn't store it in num. And in the meantime, process J calculates the same token, so they have the same token number because they came at the same time. So it has the same token, but it stored it in num, and then it started checking all the other processes. If that is the case, then when it checks process I, it will not check its most updated token. It will see that process I's token is 0 because I didn't yet store the token into num. Now if process I's token is 0, then it will bypass the process I. It will bypass the process I and will go into critical section. Process J goes into critical section. Now if process I gets CPU cycles and it stores the previously calculated token into num, Now when process I checks all other processes, it will see that J has the same token, but I is less than J. So it's process I star. So our process I also goes in. So both process J and I are in critical section. That was the problem we had. And there was an easy fix to the problem. The easy fix was that, okay, don't let process J check all other processes until process I has stored the token into none. So that's why we have those choosing variables. So what do we do with choosing? Whenever you try to select a token, you make choosing equals 1, and after you are done selecting, you make choosing equals 0. Right? And then process J, when it tries to check process I, it first waits on choosing. Right? It first says, okay, process I's choosing is 1 because process I has not yet stored the num. Right? It hasn't yet stored the token into num. So process I's choosing is 1, so let's wait for it. Let's wait for process I to finish. So process I then finishes, which means num of process I is updated. Now when process J checks process I, it will see that process I has the same num as process J, but I is less than J, so process J will wait for process I. So that's how we solve the problem of mutual exclusion violation by using choosing variable. So anybody here doesn't understand this, and it's okay to not understand, I can go over it again. So you try to assimilate this again, take some time. If you don't understand, come during office hours, or I will also conduct a exam review session in one of the recitations. So you can come there as well. I'll announce which recitation I'm going to go, and I'll post the video of that recitation. So whenever I announce, you can come to that recitation, but most probably it will be after spring break. Now the thing is, let's argue whether Lambert's bakery algorithm can be implemented in practice or not. Can it be implemented in practice?
Well, there's only a finite number of process IDs, so that's
Yes. So one problem is there is only a finite number of process IDs, right? It depends upon how many bits you store for process ID. If you have 16 bits process IDs, then the 2 to the power 16 plus 1 is the same process ID as process 0. So in that case, you cannot distinguish between process 0 and process 2 to the power 16 plus 1. In that case, this algorithm will not work. So what will happen? What will happen is that, let's say process 2 to the power 16 plus 1 had the same num as process 0. That they came at the same time, let's assume. If they came at the same time, they had the same num as process 0, then let's evaluate this condition, the while condition. Suppose while num j's are not 0, right, for process 0 as well as process 2 to the power 16 plus 1. So let's say process 0 is checking it. If process 0 is checking it, then I is 0 and j is 2 to the power 16 plus 1. So now so num j is not 0, and you check that condition, num j comma j is less than num I comma I, right? So now, so what will be the value of that condition? Will it be true or false? Since both the nums are same, you will compare the indices. Now you will find that the indices are also same because it rounded off, right? 0 is same as 2 to the power 16 plus 1 because you only had 16 bits. So now that condition will be false because we said that j equal to I returns false. Right? So if that condition is false, then process 0 goes into the critical section. And if you consider process 2 to the power 16 plus 1, that will also see the same thing, that I equals j. So for that also the condition will be false. So both process 0 and process 2 to the power 16 plus 1 enters the critical section. So this does not work when you reuse process IDs. If you reuse process IDs and there are two processes with the same process ID now, it won't work. So it works for limited number of processes at a particular time. That is one thing. The other thing is token. Token number, you can have a specified amount of bits for token number. Right? So if say you have 256, the maximum token that you can get is 256. Then what can happen is that process 0 or process 1 has a higher token number than process 257. The process number 257 has a lower token number than process 1. So process 1 came early, but process 257 gets access to critical section. So it leads to unfairness. It can lead to problems with starvation. So these are two of the things that are problematic. So since these are problematic, software solutions are not used. They are not used for the critical section problem. Now what is used? What is used is a very simple but a very dangerous technique. So let's and it is a hardware based technique. It's not a software based technique. So what is used typically is a hardware based technique. So this is the hardware based technique. So what you do? Basically the entry and exit code are very simple. It's one instruction. The entry code is disable all interrupts. And then you execute critical section and the exit code is enable all interrupts. So what will this serve? How does this solve the critical section problem? If you disable interrupts, how will it solve the critical section problem?
Because interrupts take care of any volatile variables. So if you disable all interrupts, then they no longer have volatile variables.
What do you mean by volatile variables?
They're basically variables that can be changed from two codes.
So shared variable.
Yeah, exactly.
No, but interrupts will not stop you from updating shared variables. Yes?
The context switcher can run.
Exactly. So if you remember, when we talked about context switch, and when we talked about maybe the second class, we said that one of the motivation of operating system is to stop processes from executing for too long, right? That was one of the motivation. Now, how did we solve that problem? We solved that by using interrupts, and we said that we'll have interrupts for every clock ticks, right? So we said that we'll switch between processes using interrupts, and the interrupt service routine was context switcher. Right? We said we'll go to TCB and update all those register values and all that. So if you stop interrupts, then that means the context switcher will not get executed. And if the context switcher does not execute, you won't switch between processes. And if you don't switch between processes, then no other process can update your shared variables while you are executing. Right? So that's the simple solution, and very crass solution, and it's a very dangerous solution. Now we'll come to why is it dangerous in a little bit. But let's understand the solution. I'm repeating. So what it does is that whenever you try to execute critical section, you will give a system call to the operating system. Right? Say that, okay, I want to execute critical section, disable all interrupts. So don't run the context switching. And then once I'm done executing critical section, then you enable all the interrupts. Now what is the downside to this?
The critical section has an
Exactly. If the critical section, that's one problem. If the critical section has an infinite loop, then what will happen? You will never come out of that process. The entire operating system is hung. Right? And you cannot do control alt delete because the context switcher is gone. If you do control alt delete, then you have to run some other process. So if you want to run some other process, you have to invoke the context switcher. That requires you to respond through interrupts. Right? But the interrupts are disabled. So you cannot even switch between processes. You cannot do control or delete. So what do you have to do? Just hard shut down. Just push the power button. That's the only way you can, or plug it out. Right? So that is the problem, that you cannot have too big of a code in critical section. If you have a big critical section, then your system will become unresponsive. Because now it won't recognize keyboard strokes, it won't recognize mouse movements. So your critical section has to be very short critical section. Now another problem with this is that let's say you have a multi-core system, not a single core. If you have a multi-core system, even if you disable interrupts, still processes are running on other cores. You cannot stop processes from running on other cores. You didn't switch, fine, but you don't need to switch in order to run processes on other cores. So if you, in a multi-core system, if you take this approach, that to solve the critical section problem, I will disable interrupts and enable them again. Right? This will not work because other processes are still executing in some other core. Okay? So this does not work for multi-processing systems. Now this disable enabling interrupt only can be done in the privileged mode. You cannot do it in user mode threads. User threads cannot do it. Only kernel threads can do this kind of disabling interrupts. And it has to be a short segment because of the reasons we have already talked about. And it is problematic because yes, you will miss interrupts. You will miss interrupts which your system will become unresponsive if the critical section is too long. And it does not work for multi-core systems. Because for multi-core systems, for parallel computing, you don't need switching. You don't need switching. You just run 4 threads in 4 cores. So it won't, those threads can update the same shared variables. So there will still be rest condition, even if you have disabled interrupts. So this only works for single core systems, and it only works for kernel threads. You cannot do it for user threads. So now this interrupt disabling is used by many functions. There are 3 different types of functions that use interrupt disabling to do critical section, to solve the critical section problem. Yes.
Why can't this solution be used for user level threads?
It's not. It can be, but you don't use it. I mean, it's not allowed to use in user level threads because user level threads are written by programmers who are not part of the operating system development. Yeah. Okay. So now this interrupt disabling, when you think of a single core system and you disable interrupts and run something and then enable interrupts, so whatever you run in between, there is no switching, right? You cannot switch. So if you have 3 instructions, 4 instructions, all those instructions are run without switch. So that kind of execution is called atomic execution. Atomic execution means that there are some lines of code which are executed without switching. These are not single instructions. These are multiple instructions. Right? These are multiple instructions that are executed one after the other without switching. So this is called atomic execution. So when you disable and enable interrupts, then you get atomic execution. Now the thing is, the operating systems, they have the people who develop operating systems, they have decided that this is not for user level threads. Right? So these are only for kernel level threads, and you will have specific functions that you can call. And what goes or what is executed in that critical section is also controlled. You cannot execute anything you want in that critical section because of the reason that you might execute an infinite while loop and it will cause problems to your operating system. Right? So these are the 3 things that you can do. Test and set, compare and swap, and exchange. These are the three you can call them like APIs, atomic APIs, you can call them. Not really APIs, these are functions, but these are atomic functions. So you can only do these three things. Now test and set, compare and swap, exchange is basically a practical implementation of test and set. It is used in Intel cores. In Intel instruction set, exchange instruction is there, and that exchange instruction is atomic. And how does it do atomic? By enabling and by disabling and enabling interrupts. So you need some hardware support. So this exchange is a practical implementation of the test and set that we are going to use. So I won't discuss compare and swap, it's kind of similar, but I will discuss test and set, and I will show you the inner operation of exchange. But you don't need to understand exchange, because it's like a industry standard atomic instruction code, right? But we will talk about test and set. We will use test and set extensively in homeworks or in tests. So let's see an example of atomic instruction. So this is test and set. So what is it? This is conceptual. This is not the actual implementation. Conceptually, test and set is this. So what you have is you have a variable x, right? You have a variable x, and you pass the address to that variable to test and set. Now, if you pass the address to that variable, then what does test and set do? Test and set returns an integer value, and this variable x has to be an integer. The variable x has to be an integer, and you pass the address of that integer. So what does test and set do? Test and set first takes a temporary integer variable, gets the value at x, right? It gets the value at x, and it stores it in temp. It's a temporary variable. Then sets the value of x to 1, and it returns temp. And it does these three instructions, these three different instructions atomically, which means there is no switching. You cannot switch while you are running these three instructions. So that is test and set. It's one example atomic function. And the exchange, as we will see, implements this. And this exchange is used in Intel instruction set. In your laptops, if you have an Intel core. So, what is the advantage? What is the advantage of having test and set here? So let's try to understand what is the advantage. So let's say I have an integer variable x, and I have initialized it to 0, and this is shared among thread T1 and T2. These are shared. Now let's say T1 does, so T1 has a variable int y locally, and it does y equals test and set. Let's say T1 does this, and then it prints y. The same thing is done by T2. No. See, if these are two threads, then they should have the same code. So they both execute together at the same time. What will be the possible outputs? there will be two outputs, right? So what will be the possible output? So let's say instead of just printing y, thread 1 prints this. What will be the possible outputs? Just think about test and set. Yeah.
Would it be thread 1, thread 2, 1 as the top output?
So you are saying thread 1, 1, and thread 2, 1. So he says that this is one possible answer. What is another? Anybody have anything else?
Thread 2, 1 and thread 1, 1.
Okay, so just the reverse. Yes.
Thread 1, 0, thread 2, 1.
So the second option is thread 1, 0, thread 2, 1. Any other?
Reverse.
Reverse. Any other solution?
Would
Yes.
would you just have alternate one, you would have 1, 1, 0, 1, 1, 0, 0, 0, and the possibilities reverse all?
Just execute once. It's not a while loop.
Yeah, I mean, that's all possibilities, right?
Which
So
one?
we get 8 total possibilities.
So what are the other 4?
No, other 2. So it's 1, 1, 0, 1, 1, 0, 0, 0, and then all of those.
0, 0? Okay. So what you have? Thread 1, 0, thread 2, 0. And yeah. This is another option. So let's analyze what happens. So let's say thread 1, let's assume, because these two threads are executing together, we don't know which one executes first, which one second, we don't know. So that's why we have those arrows, that it might be either one. So let's say thread 1 executes first. So thread 1 executes first and thread 2 executes afterwards. So then what happens? So if thread 1 executes first, so it says int y, y equals test and set ampersand x. What is the return value of test and set? 0. Why? Because if I give test and set ampersand x, then you go into that function, so temp becomes 1. No, sorry, temp becomes 0, because value of x is 0 right now. So temp becomes 0, and then it sets x to 1, and then it returns temp, which is 0. Right? It returns temp, which is 0. So y becomes 0. So thread 1 prints 0, and then let's say thread 2 executes. So thread 1 prints 0. So we are looking at these two, 2 and 3. We are looking at 2 and 3. So thread 1 first prints 0. Then let's say thread 2 executes. So if thread 2 executes, it does y equals test and set ampersand x. What happens? What is the return value? So they say 1, somebody else says 0s. Why? What? So why 1?
Because temp is set to x, which has been set to 1.
So if you think about the first time you execute test and set, if you think about that, then temp becomes 0, right? And the next line is the value at x becomes 1. Now this is value at that address, right? So which means this is not a local variable anymore. You are changing the value of that global data x. So after you execute the first time, the x becomes 1. So now if you execute the second time by thread 2, then you see that okay, temp equals value at x. What is value at x? It's 1 now. Right? And then again you set value of x to 1. So value of x remains 1. And then you return temp. So you return 1. So the next time thread 2 executes, thread 2 sees y equals 1. Right? So it prints thread 2 equals 1. Thread 2 1. So number 2. So now we are looking at number 2. Right? If thread 1 executes first. Now what happens if thread 2 executes first? You switch. Thread 2 gives 0, thread 1 gives 1. Right? Anyways, what you will get is either, so if thread 2 executes first, then thread 2 will give me 0 and thread 1 gives me 1. Right? Now if I remove this text, and only see the status of the variable, there is only one solution, 0, 1. Right? So there is no uncertainty. Yes, you had something?
Couldn't we switch between the threads in between setting the value of y and printing?
No. So, pardon, which one?
Between setting the value of y and printing, couldn't we switch
Oh,
between
yeah.
threads?
That you can.
So in the case of thread 2, 0, thread 1, 1, we could also get thread 1, 1, thread 2, 0, if it switched between printing.
Remember, y is a local variable. Y is not shared.
Yes.
So if y is not shared and you switch, it will get the same value as it was in thread 1. So what is your situation here? So thread 1 has computed 0 and then thread 2 has computed 1. But then you switch and you are saying that thread 1 will now print 1.
No, it'll still, I'm saying if it doesn't switch, then it would print thread 1, or thread 2, 1, and then thread 1, 0.
Yeah, that's we have the first one. Right? Yeah, so this can also switch because thread 2 can print before thread 1. Yeah, that can happen. Yes. So this is the characteristics of the test and set. Right? So now let's see. Yes.
Did we say that it couldn't be number 3, or?
It couldn't be number 3.
But what if you? Oh, wait a minute. So you're saying that when test and set is being run, that's when the context switcher is disabled?
Yes, because that is atomic.
Uh,
That's when you disable all interrupts, and then after you have run the test and set, you enable it. Right. So it cannot be 1, it cannot be 3, it can only be 2, and there are different versions of 2, like different combinations of 2 can be there. Now the only thing that, or the one important thing that you want to notice here is that there is lesser uncertainty. Why? Because one thread is getting 0 and the other thread is getting 1. Doesn't matter thread 1 or 2. Doesn't matter. But one of them will get 0 and the other one will get 1. There won't ever be the case that both get 0 or both get 1. Right? Now which one gets 0, which one gets 1, you don't know. There is that uncertainty. But there is never a case that both get 0, both get 1. So whenever two threads at the same time execute test and set, then both these threads will get different values of the shared variable. So can you use that property to solve critical section problem? How will you solve the critical section problem? Using this property that whenever two threads at the same time execute test and set, they get different values. How will you solve it? Can you give me an answer? What is the entry code? What is the exit code? So let's So let's write it here. So there is a thread T1 and there is a thread T2 and you have a critical section here somewhere and you have a critical section and you have to write something here entry code and something here exit code. What will that be? So what is the exact pseudocode?
You just want to use this property as a way to get something for every process.
Yeah, well, we want to use that property to have mutual exclusion. Because we know that two threads are getting different values. So how do we configure it? Yes.
So like you do test and set, and then you do like a while loop to check if it's equal to the other one. And
Kind of, yes. So what we do is we have a variable int, so this is shared, right? So this is a shared variable, int x equals 0, let's say. And then what you can do here is you can say while right? Will this solve the critical section problem? Will this solve the critical section problem, this solution? Will we have mutual exclusion? Let's analyze. So if two threads come at the same time, x is initially 0, if two threads come at the same time and they execute that while loop, right? They try to test that condition. So if they try to test that condition, we know that if two threads execute test and set at the same time, they get different values. So one will get 0, the other will get 1. Whoever we don't know. So whoever gets 0 breaks from that while loop. Two processes cannot break the while loop at the same time because they are getting different values. So whoever gets 0 breaks the while loop, the other one remains there, stuck. It executes the one which breaks the while loop, executes critical section, and then finally lets it go, x equals 0. Lets it go. Now thread 2 is, if thread 1 got x equals to 0 initially, then thread 1 will break and go into critical section, then thread 2 has a chance, right? Thread 2 has a chance, but thread 1 can go again if it wants to. Yes.
Oh, so there is starvation then, because I was going to ask for a possibility for that.
Okay, we know there is mutual exclusion. Is there starvation? What does starvation depend on in this case? Yes, keeps on looping, but no, not the critical section, I mean the threads. The threads keep on looping. So if I have like a while 1, right? They are coming back. The threads are coming back. But what does, so if the threads come back again and again, there is a chance that the thread 1 will get into critical section again and again. But what does that chance depend on? Who controls that chance? Not test and set. Test and set doesn't control the chance. It's the chance that you will execute test and set when x equals 0. Right? If you execute test and set when x equals 0, then you get critical section. But what is the chance that you execute test and set when x equals to 0? Who controls that chance? The context switcher. And we are assuming the context switcher is fair. Right? We are assuming that the context switcher is fair. So if the context switcher is fair, there is no starvation. So the key to get rid of starvation in your algorithm is to somehow configure your algorithm so that the starvation depends upon context switcher, and assume that the context switcher is fair. So this solves the critical section problem. You have bounded waiting, you have progress, because if thread 2 doesn't want to go, then x is always 0. So thread 1 always goes, right? So you have progress, you have bounded waiting, and you have mutual exclusion. But this is not a software solution. This requires hardware interruption. So hardware, some specific hardware. So test and set is the hardware bit that is needed. Atomic instructions are a property of the hardware. It's not a software problem. Yes?
Will this work for more than 2 processes?
Will it? Okay. So his question is, will this work for more than 2 processes? So if you have a third process, let's say you had a third process. Will it work? Will it have mutual exclusion between all 3?
Yeah.
So what will be the status of X? What will they see if all 3 execute test and set at the same time? Only one will get 0, all others will get 1s. So maybe this one gets 0, this one gets 1, this one gets 1. Whoever gets 0 goes. Right? So this sets the tone for our next topic, which is semaphores. So semaphores are a data structure, you can say, which makes use of this hardware-based critical section problem, a solution to that problem. And then using that, we can synchronize processes. We can say that process 1 goes, then process 2, then process 3. We can synchronize them. So we'll talk about that next time. Tell them to fix their document. Where is the phone?
About the second model.
Yes.
That breaks the condition. Because doesn't that just return it anything?
Yeah, so you can see 0 or 1 as a truth value.
Oh, okay.
So
That
if
makes
it's
sense.
0 it's false, if
Yeah,
it's 1
okay.
it's true.
Okay, good. Thank you.